Okay, so we're going to talk more about classical mechanics. It's been a while, but let's get to it. So the way that I'm going to do this, the way I've done it previously, is I've just been kind of noting down the important parts of the section, and I've been kind of talking about that. But I think maybe a better way of doing this is I have the PDF here. There it is. I have the PDF here, and if you look at my notes here, I've taken notes for different sections, different parts. I have more to go, but I thought maybe the better way of approaching this is just share my notes with you and talk about it, mention what I think is important, and also go over some of the stuff that maybe the book doesn't really go over as much. Sometimes they'll just kind of do something and expect you to know it, and obviously that can be hard for students sometimes. So I'm just going to go over this stuff, just like we're going through notes together, and I'm hoping that that'll be somewhat helpful. I'm not sure why it's not letting me scroll. Okay, so we're going to talk more about classical mechanics. It's been a while, but let's get to it. So the way that I'm going to do this, the way I've done it previously, is I've just been kind of noting down the important parts of the section, and I've been kind of talking about that. But I think maybe a better way of doing this is I have the PDF here. There it is. I have the PDF here, and if you look at my notes here, I've taken notes for different sections, different parts. I have more to go, but I thought maybe the better way of approaching this is just share my notes with you and talk about it, mention what I think is important, and also go over some of the stuff that maybe the book doesn't really go over as much. Sometimes they'll just kind of do something and expect you to know it, and obviously that can be hard for students sometimes. So I'm just going to go over this stuff, just like we're going through notes together, and I'm hoping that that'll be... Okay, so let's go ahead and talk about it. So it says first, if you remember, we talked about air resistance prior. We're going to talk about linear air resistance for just this section. Now it says first, let's consider a projectile that has quadratic force that's negligible. So you don't have to worry about that quadratic part that we talked about in the previous video, just the linear part. It says we'll see that because the drag force is linear, the equations of motion are very simpler to solve. So they look at, for example, my Apple Pen's almost dead, so I'm going to try to let it charge a little bit longer. But what we have here is we have this particle, and gravity's working on it, and there's this drag force opposing motion. So that's kind of what we're looking at here. 28% now, that's good. Well, Newton's second law says mass times the second derivative of position, which is just acceleration, is our force. Or mass times acceleration is equal to... Now, what it looks like they're doing here, and this might trip people up, is they're letting down be positive. Okay? So in this case, we would say gravity is actually positive because it's pointing down, to where the drag force has a component velocity as well, and that's going to oppose our motion. So that appears to be what they're doing there. It says it's an interesting feature of this form is that because neither forces depend on r, that's just your position, the equations of motion does not involve r itself, only the first and second derivative of r. In fact, we can rewrite r double dot as v dot. So those are both acceleration. Sorry about that. I have a dog going crazy because he doesn't like the cat. Anyways, hopefully you can't hear it too bad. Okay, so yes, mass times the first derivative of velocity is mg minus bv. where g and v are vectors. G is obviously pointing in the y direction, and v has components in both the x and y direction. So it says this is now a first order differential equation for v. This simplification comes about because the force depends only on v, your velocity vector, and not r. So if it depended on r, then it wouldn't be a first order differential equation. It would be a second order differential equation because acceleration is the second derivative of position. And when we say first order, that means the highest derivative you have is the first. If it was acceleration, it would have been a second order differential equation because acceleration is the second derivative. So it means we only have to solve for a first order differential equation for v and then integrate v to find r. And it says the most important simplification feature of linear drag is the equations of motion separate into components especially easy, with x measuring to the right, so that's positive x, and y vertically down. So velocity mass times the second derivative of velocity in the x direction is just minus vx. There's no other force acting in the x direction other than that. And your mass times your first derivative velocity in the y direction, well, that has gravity, which we're saying is positive, and velocity, which we're saying is negative because of the direction we chose, so minus bvy. And it says we have two separate equations, one for vx and one for vy, where the equation for vx doesn't depend on vy. So if you look at 2.15 and 2.16, 2.15 has vx in it, but no vy. And that makes the differential equation a lot easier to solve. And for 2.16, they have it in terms of vy, but there's no vx in there. And it says if the drag force was quadratic, we know that's minus cv squared, your velocity is going to be the square root of your component squared, right? That's how you find the magnitude. Then in 2.14, you'd have to replace minus bv with all that nonsense. But let's not worry about that because that's not what these problems are going to have. That'll be something we'll see later. So it just shows you it gets much more complicated because each equation will involve velocity in the x and velocity of y. And they're saying these are called coupled differential equations, where you have these mixed variables in them, and it's definitely a pain compared to what they're calling uncoupled equations, which are what we're seeing in 2.15 and 2.16. They're not married, they're independent. And then it goes on to say that because they're uncoupled, you can solve each equation for linear drag separately, and then you can put the two equations together. So they looked at an example with a cart moving to the right, and it'll have a drag force to the left. And they're going to solve this differential equation. It starts off by saying at time 0, we're looking at it at x0, and the initial velocity is just vx. Now, if we're to look at the free body diagram, there's really not much to draw. The only force acting in the x direction is drag. So the velocity in the x direction is equal to k vx. Now, we probably just saw it just earlier as this, right? Well, if you divide over by the mass, you get minus b over m vx. And what they're doing, I don't want that, I want this. What they're doing is they're saying this part is just k, without the negative. The negative should be out front. So then you can say v dot x is just minus k Vx. Draw that k a little nicer. So that's where that's coming from. And then it mentioned k is a temporary abbreviation for b over m. This is a first-order differential equation for Vx, whose general solution must contain exactly one arbitrary constant. Okay, so if we were to look at this and we wanted to solve for velocity, what we have is we'll do it in, I guess, blue. You have a function and that function's derivative. So what it's saying is if I take this function and I take its derivative, it's equal to itself times some constant. So there's a lot of different methods for solving different differential equations, but this one you can kind of logically see, hey, what if I take its derivative? I end up with just a constant times whatever I took the derivative of. And that has to be e, right? If I take the derivative with respect to time of e to the kt, that's just k e to the kt. Okay? So we know for a fact that to solve this differential equation, I used k. I guess that's not good because they had k earlier. I'll use a like they did. It's just a e to the kt. And in this case, this was negative, right? Which means you're going to have that be negative still and the negative there. You could put a negative in front of the a, but a is just a constant, so there's no point. Why did I change that to k again? Oh yeah, these were k. They just put the constant out front. A is a constant, so you really don't have to worry about that negative. Draw that k a little nicer. So we know that the velocity has to be ae to the minus kt. Now that's what's called the general solution because we don't know that constant a. But earlier in the problem we were given these initial conditions for time. Oops. The time and the position here and the velocity. So what we know is we have velocity in the x direction, not y, t is equal a to the e minus kt. Now, at t equals 0, velocity in the x direction is just v naught x. So, v naught x is equal to a e to the 0. E to the 0 is just 1, so that's our constant of integration. So now we can solve the particular differential equation, and we know what a is equal to. Let me draw the little box. That's not what I wanted to do, even close. Why is my thing being ridiculous? Okay, I'll box it then, manually. It turns into just v naught x e to the minus kt. And then he introduces the fact he doesn't use k anymore. What he does is he says tau is 1 over k. So tau equals 1 over k, which equals, what did we say k was? We said k was b over m. So this is m over b, another way of thinking of it. And he just puts that in there. Okay, let me draw that a little nicer. Okay, so that's all he did there. Now graphically, if you were to graph this, you would get this graph. So you start off with an initial velocity and you slow down. that makes sense because that's kind of what we see in the real world. One of the reasons Newton's first law is kind of anti-intuitive is because you think, hey, if I roll a ball, eventually that ball is going to come to rest. And Newton's first law says an object in motion will stay in motion, with the caveat being unless there's an external force. Well, there is an external force in the real world. There's drag. That's why it seems kind of weird at first. And this shows it. This actually shows more of what we see in the real world. Likewise, if you wanted to, you could integrate this guy again, and instead of v of x, you could get x of t. Okay, so we can do the exact same thing. We just have to integrate it again. And what do we get? Well, this will be minus tau e to the minus t over tau. Now, what do? You keep everything this when you're integrating e, you keep everything the same, and you divide by this part. But tau's in the bottom, so if you're dividing by tau, you just flip it. Not t though, because that's what we're integrating with. So we're just looking at the other constant. And if there was nothing there, if it was just minus t, then you get back to where you were. We're just doing that because of the exponent. Now, what are our limits of integration? We're gonna go from 0 to t. 0 to t. And if we work through this, you'll see it becomes minus v naught x tau e to the minus t over t, right? Or minus t over tau, sorry. Minus, or plus, because that goes away, v naught x tau e to the 0 is just 1. And now we can factor out v naught x tau, and you're left with 1 minus e to the minus t over tau. And what they do in the book is they let this whole stuff, they just let that equal x sub infinity. So you can say this differential equation is equal to x sub infinity, well, it should be parentheses, 1 minus e to the t divided by tau. And that is this part that he got. Also, I want to talk about the use of dummy variables. Don't worry about that so much. That's really to make the analysis a little easier. But as far as I know, that's not going to be something you really need to worry too much about. So graphically, if we were to graph this, let's see, I did it in blue, you get this graph. And you're approaching this asymptote of x sub infinity. That's why they used this notation, because this is the position you're kind of coasting to, your final position, if you will. So yeah, we see that that's where that's approaching. And now we're going to do the exact same thing with vertical motion. And we're going to introduce the idea of terminal velocity. So if we were to look back at the free body diagram up above, y is a little more complicated because you have two forces, right? You have a component for the velocity, or I'm sorry, drag, and you obviously have gravity working down. So your mass times acceleration is mg, because of how we let down be defined, minus bvy. Now, the idea of terminal velocity is when you're not accelerating. You reach your maximum velocity. So there's no acceleration, and we can see mg is b vy, or velocity y is mg over b, or what we call v terminal. So terminal speed, it says, is the speed at which our projectile will eventually fall if given time to do so. It depends on m and b, so it's different for different bodies. So if you have the same shape and same size, but one is heavier, it'll have a higher terminal velocity. So if you dropped a bowling ball and a feather in a vacuum where you don't have to worry about this, we see that they fall at the same rate. But when you incorporate drag, mass is important. And that's where you see what you would expect to see, because that's what we see every day. Well, I don't know if you see bowling balls fall every day, but you know what I mean. And also, we can see that the terminal velocity is inversely proportional to the coefficient b. So if you have larger air resistance, you're dividing by a bigger number, you're going to have a smaller terminal velocity, which, again, that makes sense. Then we're going to go through this example problem here next. Okay, so we're going to continue here. Sorry, I went to go get some food. But we're going to look at this example about terminal speed of a small liquid. So it wants us to find the terminal speed of this tiny oil drop, and it gives us the diameter, the density. It wants us to do the same thing with a different, not density, but diameter. Now, the solution they did here, it looked kind of weird to me, so I'm gonna, I've wrote all over the place, but I guess I can just do it right over here. So we know the equation for the terminal velocity is mg over b. And we know b is beta times d, the diameter. And we know density, which I guess I'll call here, is mass divided by volume, or the density times the volume is the mass. Okay. Well, let's plug some stuff in. So the terminal velocity is equal to d times the volume. So the volume will be what? 4 pi r cubed. But instead of r cubed, we're going to do diameter, cut it in half here, squared. All divided by 3. Now, the density, they tell us, is just, they give us some symbol. I don't remember. Maybe it was rho. So if we work this out, oh, and then also we have B, which B is BD. So we get this density times 4 pi. This should be cubed, sorry, 4 pi r cubed. D cubed all over 8 all over 3b d. Let's see, we can simplify this a little bit, right? This should be cubed now. Boom, boom, 2. And you should get V terminal is equal to, well, we have our rho density. We have pi. We have d squared. Also, there should be a g out front from here. So I'm just going to carry that along. G divided by what? Well, we have a 2 and a 3. So if we flip that, that's 3 times 2 is 6. And then B. Let's see if they'll let me do my shapes now. Hey, it did. Cool. So then you just have to plug in everything else they gave us, or as a constant. So all you have to do is plug in the values you want, and you'll get your answer. So that's these parts. So now we've discussed the terminal velocity of a projectile moving vertically, and now we want to see what happens as it approaches that speed. Now, I also want to explain how they got this equation, because I could see how that could be a little confusing. So what we have is this from previously. Now, it might seem kind of weird, but factor out a negative b from all of this. So you would get mg over b, I guess that would be negative, plus vy. Now, the important thing to know is that this is our terminal velocity. So we can rewrite this. I'm going to put the vy up front minus v terminal. And that's what they got here. That's here. So now what it wants us to do is solve this differential equation. And again, there's different ways to solve it, but the big thing to do is a substitution where you let u equal vy minus v terminal. If I were to take the derivative with respect to time, well, the velocity is changing, but v terminal is a constant. So that's 0. So u dot is just equal to v dot. So in other words, we can say m u dot instead of v dot is equal to minus b times u. Well, this probably looks very similar, and that's because this was the same problem we solved before, where you have a function and its derivative with constants multiplied. So all we need to do is look back at the previous problem we did, and we should see the solution for this is u equals a e to the minus t over tau. It's the exact same one as the vertical solution. Okay, so hopefully we've done that before, and we know what u is. U is the vy minus v terminal equals a e to the minus t divided by tau, or our velocity is v terminal plus a e to the minus t over tau. Now, real quick, I'm going to come over here and show what happens when t equals 0 and velocity is going to be v naught y. Well, what do we have? Our velocity, we said, is v naught y minus v terminal equals e to the 0 is just 1. So what we do is we solve for a. So now we can say vy is v terminal plus v naught y minus v terminal. I guess I'll just put t. Sometimes I'm doing TER, sometimes I'm just doing t. Hopefully you guys know what I mean, though. E to the minus t over tau. I can distribute that e, v terminal minus v terminal e to the minus t over tau plus v naught y e to the minus t over tau. Both these terms have v terminal in it, so I could factor that out, and I could say vy equals v terminal 1 minus e to the minus t over tau plus we have our v naught y e to the minus t over tau. That's also a way you can write this, and that's also totally fine. Let me see how they did it. They did, yeah, that's what they did. They factored out v terminal, And then they showed graphically what happens. Well, if you were to graph that, you'll get something like this. And we see we approach this terminal velocity. So as t goes to infinity, you approach your terminal velocity. They also do the case where v naught is 0, in which case this part just goes away. So you're left with just this. I don't think that's too crazy. Now, it says we see that the velocity starts out from 0 and approaches a terminal speed of v terminal as t approaches infinity. Now, it says that tau for a falling body is easy to see. When t equals tau, so you just plug, that's 1 minus e to the minus t over t, so that's e to the minus 1. You get 0.63 terminal. In other words, you reach 63% of the terminal velocity. And if you plug these different values in for tau, you can get different percentages for the terminal velocity. So that's kind of the key thing here. We'll do the next equation here as well. Okay, so there's one other example problem that's pretty straightforward. It just wants you to find the characteristic time, which is what tau is, for the oil drop in the previous experiment. So that was the last example we did. It tells us tau is m over b. Okay, well, we know v over t. I actually worked it out over here. We know v over t has the exact same definition with the exception of a g. So our terminal velocity, or I'm sorry, tau, is tau times g, because tau covers this part. Let me do red. Tau covers this times g. And a little bit of algebra, and we can find that tau is v terminal over g. And then you just plug in the values. We already found the terminal velocity, so that's not too bad. For this one, it requires you to do a little bit of integration. So we have velocity as a function of time is equal to v terminal plus the y naught minus v terminal times e to the minus t divided by tau. If we want to find position as a function of all this, what we want to do is integrate. Okay. Well, this will give us our position y as a function of time, v terminal times time, because that's just linear, plus, I'm going to go a little slower here, vy naught minus v terminal times the integral of e to the minus t over tau dt. Well, we want to divide by whatever is in the denominator, so that'll be minus tau. So you multiply by minus tau. And then, of course, it's exponential, so you keep whatever the original function was and evaluate it from t equals 0 to t. Well, v terminal t minus tau, vy naught minus v terminal, that's going to be e to the negative 1, and then a 0 will just be 1 itself. So e to the minus t over tau, we're just plugging that in, minus e to the 0. Well, e to the 0 is 1. So I'm going to do a little bit here. I'm going to factor out a negative to make it plus tau. And then I have 1 minus e to the minus t over tau. And now we have the y component of position. We found the x component somewhere. Oh, up here. So now we have two equations that describe position for linear drag. And that's this. So awesome, we got it, we did it, and that's the section.